I'm not going to start with a light switch this time, because you've heard that before, and your brain already knows how to ignore it. Instead, I want you to picture something much quieter, something almost unsettling if you really let it sink in. Right now, at this exact moment, you are not seeing the world as it is. You are seeing a version of it that is already gone. The screen in front of you, the walls around you, even your own hands, everything you perceive arrives to you slightly late, carried by light that needed time to reach your eyes. The delay is so small that your brain edits it out completely, stitching reality together into a seamless present. And because of that, you grow up believing something that feels obvious and unquestionable, that what you see is happening now. But it isn't. It never has been. Now here's where I want you to slow down and really think, because this is where the illusion begins to take shape. The reason you never notice this delay is not because light is instantaneous, but because the distances in your everyday life are absurdly small compared to the speed at which light moves. A photon crossing a room takes only billions of a second, far below the threshold your brain can detect. So your mind does what it always does when faced with something too fast or too small. It simplifies. It rounds it down to zero. It tells you a story that feels clean and intuitive. Light has no travel time. The world is immediate. Cause and effect happen together. And once that story settles in, you carry it with you everywhere, using it as the foundation for how you imagine space, distance, and connection. But I want you to notice something subtle here. Something that changes everything if you follow it to its conclusion. Your entire intuition about speed is built on a lie of scale, not a mistake in physics, not a flaw in the universe, but a mismatch between the size of your world and the size of reality. On Earth, light behaves like magic because the stage is too small to reveal its limitations. Distances are measured in meters, kilometers at most, and at those scales, light might as well be everywhere at once. It circles the entire planet multiple times in a single second. It crosses continents faster than your nervous system can register pain. It outruns every process. Your body is capable of perceiving. So of course it feels instantaneous. How could it not? And this is where I want you to catch yourself, because this is the exact point where your intuition betrays you. You take that everyday experience, the room lighting up instantly, the world appearing continuous, and you quietly extend it outward without realizing it. You assume that what feels true on Earth must remain true everywhere else. You imagine light as a perfect bridge, something that connects places across space without meaningful delay, something that makes the universe feel reachable, almost intimate, as if distance is just a larger version of what you already understand. But that assumption is never tested in your daily life, so it never breaks. It just sits there, invisible, shaping the way you think about the cosmos. What you don't realize is that this instantaneous feeling is not a property of light at all. It is a property of you. It is a limitation of your perception, a consequence of the narrow range of distances you evolved to navigate. Your brain was never designed to understand astronomical scale. It was designed to help you survive on a planet that is tiny compared to the universe. And so it gives you a useful illusion that space is manageable, that signals move quickly enough to ignore delay, that everything you see is happening now. That illusion works perfectly until you step outside the boundaries of your everyday experience. And when you do, something strange happens. The thing you trusted most, the thing you thought was your fastest connection to reality, begins to reveal itself as something else entirely. Not infinite, not immediate, Just very, very fast and suddenly. Not fast enough. Now I want you to take that feeling you just had, that quiet realization that everything you see is slightly delayed, and stretch it. Because this is where your intuition begins to fail in a way that is not gentle or gradual, but abrupt and almost violent. As long as you stay within the scale of your daily life, light behaves like perfection, like something that erases distance entirely. But the moment you begin to widen the stage even a little, the illusion starts to crack in ways your brain is not prepared for. Let's begin with something still close enough to feel familiar. The moon hangs above you, calm and immediate. Something you could almost believe is just there, but the light leaving its surface takes about 3 seconds to reach your eyes, which means when you look at the moon, you are seeing it as it was more than a second ago. Not now. Not ever now. And even though that delay is small, you can already feel something shifting. Because for the first time, distance is no longer invisible. Now push a little farther. The sun, the source of nearly all energy on Earth, feels constant and present, something that defines your day in real time. But the light warming your face left the sun 8 minutes and 20 seconds ago, long before you stepped outside, long before you even decided to look up. And this is where the idea begins to stretch in a way that is harder to ignore. If the sun were to vanish this instant, you would not know. The sky would remain bright. The warmth would continue. For 8 full minutes, reality would be lying to you, showing you something that no longer exists. And you would have no way to detect the difference. What you experience as now is already history, and still. Your intuition tries to hold on, because 8 minutes is nothing in the context of a human life. You wait longer than that for a cup of coffee. So your brain quietly compresses it again, smoothing it out, refusing to treat it as a serious delay. But then we step just a little farther, and this is where the collapse begins. Mars, the next world we have placed machines on, sits at distances that change constantly as both planets move, sometimes as close as a few minutes away by light, sometimes over 20 minutes. And this is no longer something you can ignore. When a rover on Mars encounters a problem, the signal telling us what happened takes minutes to arrive. And the command we send back takes minutes more, which means every decision is delayed, every action disconnected from the moment it is meant to control. And for the first time, you see clearly that even at the speed of light, communication begins to break down. Now continue outward, because this is where your intuition does not just bend, it shatters. The outer planets stretch those delays into hours, and spacecraft like Voyager, drifting at the edge of the sun's influence, take nearly a full day to send a signal back to Earth, a message traveling at the absolute maximum speed allowed by the universe. And yet it crawls, it drags, it feels slow in a way that should not be possible for something we once thought of as instantaneous. And still, unbelievably, we are not even close to leaving home. The solar system, vast as it feels, is a tiny bubble, a neighborhood, barely the first step into something much larger. Then comes the jump your brain is not designed to make. The nearest star system, the closest possible destination beyond our sun, is over 4 light years away, which means that light itself, moving as fast as anything can move, takes more than 4 years to cross the gap. And suddenly the scale explodes into something your intuition cannot track. A message sent today would not arrive until years have passed. and a reply would take years more, turning even the simplest exchange into a decade-long conversation. And this is not a distant, exotic target. This is the closest star, the nearest neighbor, the cosmic equivalent of the house next door. This is the moment where everything you thought you understood about speed begins to unravel. Light has not slowed down. The laws of physics have not changed. The only thing that has changed is the scale, and that is enough to transform light from something that erases distance into something that exposes it, something that reveals just how enormous the gaps between worlds really are. The same speed that made your room feel immediate now makes the universe feel impossibly large. And for the first time, you begin to see the truth that was hidden all along. Light does not connect the cosmos in the way you imagined. It only shows you how far apart everything truly is. The fastest thing humanity has ever built is already a failure. And I don't mean a small one. I mean a failure so complete that once you see it clearly, it changes the way you think about reaching the stars forever. Not because the machine broke, not because the mission failed, but because even at its absolute best, doing exactly what it was designed to do, it proves something we don't want to admire. That machine is Voyager 1, and on paper, it is extraordinary. Launched in 1977, it has been moving non-stop for nearly half a century, racing through space at speeds that would make anything on Earth seem absurdly slow, covering distances so large they are almost meaningless in everyday language. Billions of miles, beyond every planet, beyond the edge of the solar system. If you stop at that description, it sounds like success, like we have already taken the first step into interstellar space, like the journey has begun and all we need to do is keep going. But that feeling only exists because you are still thinking on the wrong scale. Because the moment you ask a different question, not how far has it gone, but how far does it still need to go, everything collapses instantly. Voyager 1 has traveled about 15 billion miles, which sounds enormous until you place it next to the distance to Proxima Centauri, the nearest star, sitting roughly 25 trillion miles away. And at that moment, the numbers stop behaving the way you expect. They don't stretch. They don't scale. They snap. That 15 billion shrinks into something almost invisible, less than 0.1% of the journey. And suddenly the most advanced object humanity has ever sent into space looks like it has barely left home. Now here's the part I want you to really feel, not just understand. If Voyager 1 were aimed directly at Proxima Centauri, which it isn't, it would take about 75,000 years to get there. Not a long mission, not a difficult mission, a time scale that erases meaning. 75,000 years ago, human civilization did not exist. There were no cities, no writing, no science, no memory of anything you would recognize as history. Everything you think of as the human story fits inside a small slice of that timeline. And Voyager would need to keep flying for all of it, and then keep going. And this is where most people try to escape, because your instinct is to say, fine, Voyager is slow. We'll build something faster. And that sounds reasonable. It sounds like progress, because on Earth, speed solves problems. But here, speed behaves differently. Even if you imagine a spacecraft 100 times faster than Voyager, something far beyond anything we have ever built, the journey doesn't become easy. It becomes less impossible. 75,000 years becomes hundreds, maybe decades, for the nearest star if you push to extremes. But the moment you move beyond that single target, beyond that one closest system, the numbers expand again. And you are right back where you started. This is the part your intuition cannot handle. You are used to problems shrinking as you improve your tools. But interstellar distance does not cooperate. It doesn't care how advanced you become. It doesn't reward incremental progress. You can go 10 times faster, 100 times faster, and the universe still feels out of reach. Because the scale you are trying to cross is not just large, it is fundamentally mismatched with anything you can build. And that is the real lesson hidden inside Voyager 1. The thing no one tells you when they describe it as a triumph. It is not proof that we are on our way to the stars. It is proof that even our best attempt barely counts as movement at all. So at this point, you might feel like you've identified the real problem. And it sounds almost comforting in its simplicity. We're just too slow. Voyager is slow. Our current technology is primitive, and once we build faster ships, everything will change. That idea feels natural because it has always worked before. Every boundary we've ever encountered on Earth has eventually given way to better engineering, stronger materials, more powerful engines. But I want you to follow this assumption carefully, because this is where the logic begins to turn against you. Not gradually, but in a way that reveals something much more unsettling. What if speed is not the solution? What if even when you push it to extremes, the problem remains? Let's grant ourselves something absurdly optimistic, something far beyond anything humanity can currently achieve. Imagine a spacecraft capable of reaching 1% of the speed of light, a velocity so extreme that no machine we have ever built comes remotely close, moving at thousands of kilometers per second, crossing the solar system in a matter of days instead of years. That sounds transformative. And in a sense, it is. At that speed, the journey to Proxima Centauri would take roughly 400 years. Not tens of thousands like Voyager, but still far beyond a human lifetime, stretching across generations, requiring a continuity of purpose that no civilization has ever demonstrated. And this is the closest star, the most favorable case, the shortest possible leap beyond our system. So you push further. You say, fine, 1% is not enough. We need 10%. Now you are entering a regime that borders on the edge of physics and engineering. A speed of 30 kilometers per second, where the journey to Proxima Centauri shrinks to about 40 years. Now it begins to feel possible, barely, uncomfortably, but within reach of a single lifetime if everything works perfectly and nothing fails. But notice what just happened. You had to push to a speed so extreme that it already strains plausibility, just to make the nearest star marginally accessible. And even then, only under ideal conditions. And now I want you to do something your intuition resists. Don't stop at the nearest star. Move outward. Just a little. A star system 20 light years away, which is still considered close in astronomical terms, now takes 200 years at that same 10% of light speed. Not a mission, but a legacy. Something that outlives the people who begin it. Something that must be handed down across generations that had no say in its origin. Pushed to 50 light years. 100 light years. And the numbers stretch again into centuries and millennia, even at speeds that already sit near the limits of what physics might allow. So you push even harder, because that is what you have been trained to do. You imagine 20% of the speed of light, maybe even higher, velocities, where time itself begins to behave differently for the travelers, where relativistic effects start to compress the experience of the journey, and yes, for the crew. Time can slow, distances can feel shorter, but this is where the illusion becomes subtle, because while time dilates for those on the ship, it does not dilate for the universe they leave behind. Decades pass at home, centuries pass. Entire civilizations can transform or disappear while the travelers are still in transit. And what begins as a journey becomes a kind of one-way separation from everything that gave it meaning. And even at these extraordinary speeds, the deeper problem remains untouched. The galaxy is not 4 light years across. It is zeta, 0, 0, 0 light years across. Even at 10% of light speed, crossing it would take 1,000,000 years. At 20%. Hundreds of thousands. These are not mission timelines. These are geological epochs. No amount of incremental improvement in speed changes the fundamental mismatch between how fast you can go and how far you need to travel. This is the point where the idea of going faster stops being a solution and starts revealing itself as part of the trap, because every increase in speed demands exponentially more energy, more precision, more protection from the environment you are moving through, and yet the reward shrinks as the scale grows. You are running faster, but the distance is expanding faster still in terms of what you can realistically cross. And that is the realization that changes everything. The problem is not that we haven't built fast enough ships yet. The problem is that even if we do, even if we push toward the edge of what physics allows, we remain confined to a tiny bubble around our starting point. The nearest stars become barely reachable. Everything beyond them remains effectively out of reach. Faster ships do not free you from this. They only let you see the walls more clearly. Up to this point, it's still possible to believe that the problem is distance, or time, or even engineering complexity. But now I want you to look at something much more fundamental, something that does not care how intelligent you are, how advanced your civilization becomes, or how long you are willing to wait. Because underneath all of this, beneath the distances and the travel times and the dreams of faster ships, there is a wall you cannot negotiate with. Not a technological barrier, a physical one. And once you see it clearly, you realize that everything we have talked about so far may actually be the easy part. The reason is simple in principle and devastating in consequence. To go faster, you need energy, and not just a little more energy, but vastly more. Because the relationship between speed and energy is not linear. It is brutal. Double your speed, and the energy does not double. It multiplies far more aggressively. And as you begin to approach a meaningful fraction of the speed of light, that requirement explodes into numbers that stop feeling real. This is not a limitation of our engines. It is a consequence of how motion itself works. Let's take something modest, something that sounds almost reasonable. A spacecraft weighing about 1,000 kilograms, roughly the size of a small car. And you want to accelerate it to just 10% of the speed of light. Not half. Not near the limit. Just 10%. Even at that speed, the energy required is on the order of 10 to the power of 17 joules, an amount so large that it begins to detach from intuition. So let me ground it for you. That is a significant fraction of the total energy consumed by an entire nation in a year, concentrated into accelerating a single small probe, not a ship, not a colony, just one object. Now scale that up to something meaningful, something that could actually carry instruments, shielding, communication systems, maybe even human life. Increase the mass by a factor of 100, and the energy scales with it. Suddenly you are talking about energy comparable to what entire countries produce annually, all dedicated to a single launch, a single mission. And that is just to speed up. You have not even considered slowing down at the destination, which requires the same amount of energy again, doubling the already staggering cost and compounding the problem further, because you must carry the fuel needed to decelerate during the acceleration phase. And this is where the trap tightens in a way that feels almost cruel. Rockets do not just need energy. They need to carry that energy with them in the form of fuel. And the more fuel you carry, the heavier you become, which means you need even more energy to accelerate that additional mass, which requires even more fuel. It is a feedback loop that does not scale gently. It grows exponentially, and this is captured in what is known as the rocket equation, a relationship so unforgiving that it turns interstellar travel into something that does not just become harder with ambition, but explodes out of reach entirely. Chemical rockets, the kind that took humans to the moon, are already at their limits, with exhaust speeds that are laughably small compared to what interstellar travel demands. Even if you move to nuclear energy, fission or fusion, which release millions of times more energy per kilogram than chemical reactions, you are still fighting an uphill battle against the sheer scale of what is required. Fusion might get you closer. Antimatter, in theory, could take you further, converting mass directly into energy with perfect efficiency. But even antimatter does not save you, because it is not a source of energy. It is a storage medium, and producing it requires at least as much energy as you hope to get back, often far more in practice. So now the problem has shifted again. It is no longer about building a faster ship. It is about generating, storing, and controlling amounts of energy that rival planetary or even stellar outputs, all for the sake of moving a relatively small amount of mass across a distance that still dwarfs your effort. And this is where relativity adds its final layer of resistance. Because as you push closer to the speed of light, the energy required increases without bound. Not just difficult, not just expensive, unbounded. This is what makes the energy wall so different from every obstacle we have ever faced before. You cannot out-engineer it. You cannot optimize your way around it. You cannot wait for a breakthrough that changes the equation, because the equation is not a product of our ignorance. It is a reflection of how the universe is built. Every kilogram you want to move at high speed carries an energy cost that must be paid in full. And the faster you go, the more punishing that cost becomes. And when you put this together with everything we have already seen, the long travel times, the vast distances, the limitations of speed, you begin to understand that interstellar travel is not just a challenge of scale. It is a confrontation with limits that do not yield, limits that force every civilization, no matter how advanced, to make the same calculation. How much energy are you willing to spend, and for how small a return? By now, you can feel the walls closing in. And this is usually the moment where the mind starts searching for an escape. Not slowly, but almost instinctively, reaching for any idea that might break the pattern we've been building. Because it feels unacceptable, almost offensive, that a civilization capable of understanding the universe could be so thoroughly confined by it. So the imagination begins to work harder, pulling out concepts that sound like solutions. Ideas that seem to slip past the constraints we've been stacking one on top of another, and at first glance They feel convincing, even inevitable. But this is the point where we have to slow down again, because nearly every proposed escape from this problem shares the same flaw. It works in theory, right up until you force it to survive contact with reality. Take generation ships, one of the oldest and most intuitive ideas. If the journey is too long for a single lifetime, then you don't try to shorten it. You stretch the mission instead. You build a vessel large enough to sustain a population indefinitely. A self-contained world drifting through space, where the people who arrive are not the ones who left, but their descendants. On paper, this sounds like a solution that neatly sidesteps the problem of time. But once you look closer, the difficulty multiplies in a way that is not just technical, but social, biological, and psychological. You are no longer building a spacecraft. You are building a civilization that must survive in isolation for centuries or millennia, recycling every resource, maintaining every system, preserving knowledge, purpose, and stability across generations who had no choice in the mission they inherited. No human society has ever demonstrated that level of continuity, not even close. And the idea that such a system could remain coherent long enough to reach another star requires assumptions about human or alien behavior that we have no evidence to support. So you move to something less fragile, something that removes biology from the equation entirely. AI proofs, machines that do not age, do not tire, do not require food, water, or air, capable in principle of operating for thousands or even millions of years. This sounds more robust, more realistic, and in many ways it is. But again, the closer you look, the more the problem shifts rather than disappears. A machine traveling through interstellar space for centuries is not moving through a harmless vacuum. It is being bombarded constantly by radiation, by high-energy particles, by microscopic dust grains that, at relativistic speeds, strike with the force of bullets. Over time, every system degrades. Electronics fail, data corrupts, structures erode. And unlike systems on Earth, there is no maintenance, no resupply, no rescue. You must build something that can endure not just years, but centuries of continuous damage. And we have never created anything remotely approaching that level of durability. Then there is the most seductive idea of all, the one that feels like it should solve everything at once. What if we don't cross space at all? What if we bypass it? Wormholes, shortcuts through space-time, tunnels connecting distant regions of the universe so that the journey becomes instantaneous. It sounds like exactly what we need. And mathematically, within the framework of general relativity, such structures can exist as solutions to the equations. But here is the critical distinction. A solution in an equation is not a technology. Every version of a traversable wormhole requires conditions that we have never observed. Forms of matter with negative energy density, exotic substances that may not exist in any usable form. And even if they do, the energy required to create and stabilize such a structure is so enormous that it pushes beyond anything we can meaningfully describe as engineering. You might then turn to warp drives, the idea of bending space itself, contracting it in front of a spacecraft and expanding it behind, allowing effective faster-than-light travel without violating relativity locally. Again, the equations permit it under certain conditions. And again, the requirements are devastating. Exotic matter, immense energy densities, configurations of space-time that we have no known method of producing or controlling. These are not hidden technologies waiting to be discovered. They are speculative constructs that sit at the edge of what physics allows, with no experimental evidence that they can exist in a form that can be used. And this is the pattern you begin to recognize. Every escape route either demands a level of stability, energy, or control that no known system can achieve, or it relies on forms of physics that remain entirely theoretical, unsupported by observation, and possibly unattainable. The more you push, the more the universe pushes back, not with a single barrier, but with a network of constraints that reinforce each other. Time, energy, environment, and fundamental law all align in the same direction, closing the door each time you try to open it. This is why the idea of a sufficiently advanced civilization becomes misleading. Advancement does not mean freedom from physics. It means operating more efficiently within it, no matter how intelligent or ancient a civilization becomes. It still exists inside the same universe, bound by the same constants, the same limits, the same structure of space-time. There is no version of progress that turns those limits off. And so one by one, the escape routes collapse, not because they are foolish, but because they are incomplete. They assume that there is a way around the problem, when in reality, the problem is not something placed in the universe. It is something built into it. Now we arrive at the question that has been waiting in the background the entire time, the one that feels almost inevitable once you have followed every step of this argument to its end. If the universe is so vast, so old, and so filled with the raw ingredients for life, then where is everybody? It sounds simple, almost casual, but it is one of the most unsettling questions ever asked, because it forces you to hold two ideas in your mind at the same time. And those ideas do not sit comfortably together. On one hand, the Milky Way contains hundreds of billions of stars, many of them older than our sun, many of them surrounded by planets. And a significant fraction of those planets exist in conditions that could support liquid water, chemistry, and eventually life. On the other hand, when we look out into that vastness, we see nothing that clearly signals the presence of another civilization. No ships, no structures, no unmistakable signs that someone else has crossed the space between stars. Just silence. For decades, people have tried to explain this contradiction in different ways. Maybe intelligent life is incredibly rare. Maybe civilizations tend to destroy themselves before they become capable of interstellar travel. Maybe they are hiding or observing quietly, or communicating in ways we do not yet understand. Each of these ideas offers a possible answer, but all of them rely on assumptions about behavior, about biology, about choices made by beings we have never encountered. And there is a simpler explanation, one that does not depend on psychology or speculation, but on the same physical constraints we have been exploring all along. They cannot get here, not because they lack intelligence, not because they lack curiosity, and not because they are unwilling to try, but because the universe itself is structured in a way that makes physical contact between distant civilizations extraordinarily difficult, perhaps effectively impossible. The distances are too large, the speeds are too limited, the energy costs are too high. Every path we have examined, every attempt to bridge the gap, runs into the same set of constraints. And those constraints do not weaken with advancement. They remain fixed, embedded in the nature of space-time. This is where a critical distinction becomes important, because it is often overlooked. There are three very different things a civilization can do across interstellar distances. It can observe. It can send signals, or it can travel physically. Observing is relatively easy. Light carries information across the galaxy, allowing distant worlds to be studied without ever leaving home. A civilization thousands of light years away could, in principle, analyze the atmosphere of Earth and detect signs of life without ever coming closer. Sending signals is harder, but still possible. Messages can be transmitted at the speed of light, crossing vast distances over years, centuries, or millennia. Communication becomes slow, but not impossible. But physical travel, the act of sending matter across those distances, is in an entirely different category. It requires energy, time, and resilience on a scale that grows beyond practicality as distances increase. And that difference changes everything. The universe may be full of observers, full of listeners, full of civilizations, quietly watching the same stars we see, detecting the same patterns, asking the same question. But watching is not meeting. Knowing is not touching. The same speed of light that allows information to flow across the cosmos also limits how fast anything with mass can follow it. And that limit turns distance into isolation. Now imagine this not as a single case, but as a universal condition. Every civilization, no matter where it arises, faces the same constraints. It looks out at the stars, calculates the distances, explores the possibilities, and runs into the same wall. Perhaps some attempt the journey anyway, sending probes or ships across interstellar space, committing vast resources to missions that will take centuries or millennia, but most of the galaxy lies far beyond even those efforts, separated by spans of time that outlast lifetimes. Cultures, perhaps even entire species. This is how the silence emerges, not from emptiness, but from separation. The galaxy does not need to be devoid of life to appear silent. It only needs to be large enough and constrained enough that its inhabitants cannot easily reach one another. Each civilization becomes an island, surrounded not by water, but by space-time itself, able to see distant lights on the horizon, but unable to cross the ocean between them. And this is the part that changes how you see everything. The silence is not necessarily a mystery. It may be the natural state of a universe where the speed of light is finite, where energy is costly, and where distances stretch far beyond what any practical journey can overcome. The paradox dissolves, not because we have found the others, but because we begin to understand why we have not, which leads to a final uncomfortable thought, one that I want you to sit with. We may not be alone in the universe. In fact, it is likely that we are not, but we may still be alone in every way that matters, separated from every other mind by distances that cannot be crossed, living out our entire history in a small region of space, while countless other civilizations do the same, each one looking up at the sky, asking the same question, and hearing the same answer, nothing. Not because no one is there, but because no one can reach anyone else.